Okay, here we have question 2. A mass m is resting at a height h above the ground. When released, the mass can slide down a frictionless track to a loop, the loop of radius r, as shown below. Part A, as a mass slides down the incline, it gains speed. However, the mass may or may not make it around the loop without falling out. Why and under what conditions will the mass travel around the loop without falling out? Why and under what conditions will it not do the loop? And explains your reasoning qualitatively, and make sure you address the normal force experienced by the mass. Okay, so a lot of my explanation is going to be verbal. I'm not going to, because it asks for qualitative, I'm not going to write out paragraphs. So you're going to have to listen now. First, let's address the issue of the normal force. As the box, and we'll just put it right there. As the box is at this point right here, the normal force is downward like this. The centrifugal force is outward like this. So maybe we can call this Fn, we can call this F sub c. And when we did these types of problems in classes, or in class or in homework sets, we always knew that the centrifugal acceleration has to be equal to mg down in order for this object to not lose contact. However, it wants us to describe this addressing the normal force. So let's be super, super obvious about this. The minimum velocity needed to get this thing to go all the way around is the minimum velocity where is a velocity at which the normal force hits zero. The normal force is this basically the supporting force directed inward. If the object is not going fast enough, it's going to lose contact, right? It's going to lose contact right here. With the top, and it's going to fall, and we don't want that to happen. So the minimum velocity has always been the minimum velocity so that the normal force does not reach zero, or I guess technically the limit at which it reaches zero. So the minimum velocity will be where the normal force is zero, and so that takes care of it. We're addressing the normal force. So, back to the first part of the question, why and under what conditions? Well, we start with PE over here, and we need to have enough kinetic energy over here at the top of this thing, because remember, it's at the top that this thing is going to fall. I mean, it certainly, I guess, could lose contact other places, but it's at the very, very top where it's at most risk of falling, we'll put it that way. So we need to have enough PE so that the KE at the top is enough. And we want the centrifugal acceleration, which is V squared over R. The force is V squared over R. Well, so we need the centrifugal acceleration to be equal to V squared over R. So when we know that the V is equal to the square root of 2gh, where h is the height that it's going to go down, because there's no friction, we don't have to worry about that. So yes, you can see that the velocity is totally dependent on the height that this thing slides down, and we need to make sure that they have a sufficient height so that your velocity at the top there is at least equal to 9.81 meters per second squared, because we need the centrifugal acceleration to equal gravitational acceleration, right? So that's under what conditions it will travel without falling out. When will it fall out? Well, it will fall out as if your velocity is not sufficient enough to give rise to a centrifugal acceleration of 9.81 meters per second squared. And so if the h is not sufficient, then the v is not sufficient, which means the a is not sufficient, and it will fall. Okay, that should take care of part A qualitatively. I did do some equations here, but it wasn't any heavy solving. They would accept that on the AP. Of course, I mean, obviously you'd have to write down words too. Part B, two fellow students are arguing about the maximum possible R of a loop so the mass can make it around. Will it be linearly dependent on H, or will the relationship have some type of power law? Without solving for the relationship explicitly, indicate a line of reasoning that would settle this argument. Okay, so all we're trying to figure out right here is the relationship between R and H. Well, let's just think about this, again, just logically. The H is, well, let me take a step back here. The height at which the object falls is proportional to v squared, right? Because the height is proportional to the kinetic energy, and kinetic energy has a v squared term in it. However, if you just think about this, and again, I'm not solving, I'm just trying to talk this out, showing some stuff. However, the acceleration is proportional to also v squared, all right, because it's v squared over r. So if h is proportional to v squared, and your acceleration, which you're eventually trying to figure out to get around a circle with radius r, is proportional to v squared, that has to mean that h has to be just linearly, has a linear relationship to a. There might be some constant in there. In fact, it's there might be some type of constant in there, but the h is going to be linearly dependent on a, and that's one way to just talk it through. Okay, so at this moment, we just ignore whatever I haven't read up there. I was trying to solve something real quickly, and it was just ignore it. It's not needed, and it's actually wrong. C. Within the loop, the normal force is always acting in a centripetal direction. Explain why the normal force is not always equal to mv squared over r at each point. Are there any points where the normal force is actually equal to mv squared over r? Support with free diagram. Okay. So let's take a look at three sort of critical points on here. Now, when we do problems in problem sets, we're almost always interested in just that point right there. So let's just examine that point right there, because that's usually where the interesting physics is happening, where the object is spinning around without falling, yada, yada, yada. So let's imagine this point right there as this thing goes around. In this case, the normal force works this way. The centrifugal force is working that way, and there's a gravitational force also working down like this way. So in this case, if you think of the directions, the normal force plus mg has to equal centrifugal force. So the normal force is actually going to be the centrifugal force minus mg. All right. Let's take a look at the bottom. What if it's on the bottom? In this case, we're going to have the normal force going up. We're going to have the gravitational force going down. And we're going to have the centrifugal force going outward as well. So the normal force is going to equal the centrifugal force plus mg. And also, what I want to point to, just to use their language, the centrifugal force is mv squared over r. Right. Well, that's just there's one other spot of interest, and that is right on the middle here, right on the side. It doesn't matter which side you pick. In this case, we have the normal force going this way. We have the centrifugal force going out like that. And note that the weight has no interest or no say in the normal force because it is perpendicular. There is no component of of gravity that works. There's no component of this mg force that works in the x direction. So in this case, the normal force has to be exactly equal to F sub c, which is going to be mv squared over r. So really only at the sides is it exactly equal to mv squared over r. That should be so that's how we do that. If the minimum height h has been found for a fixed loop of size r but a rolling ball. Okay, so what happens if you don't slide a mass? What happens if you roll it? Okay, let's make this a big red rolly ball right here. Here the key is that instead of sliding, this object is going to roll, which means some of its potential energy, the potential energy at the top, has got to be shared between its linear kinetic energy and its rotational kinetic energy. So it will not hit this bottom part here with the same linear velocity that it would have if it had just slid, whatever the past tense of that word is. It will not have the same linear velocity. And therefore, if you already have it at the minimum height, it's going to fall out of the loop. Again, one more time, because its kinetic energy, its linear kinetic energy, is going to be less because some of the potential energy goes into rotational energy, and that ain't going to help you get around the circle, especially if it's frictionless.